Hi everyone, thanks for tuning in. I'm Dr. Ben Johnson, an assistant professor at Iowa State University, and excited to talk to you today about some recent research. Before we get into that, I just wanted to recognize that I'm currently on the traditional tribal lands of the Iowa and Sioux tribes here in Iowa. We would have been on the traditional land of these tribes if we were in Montreal in person, and my field site in Montana in the US is on these tribes' traditional lands. And so to set up the rest of this talk, I'd like to ask the question for a minute about what we know about the climate in the Archean of the Earth. This is the time period from 4 to 2.5 billion years ago, early in Earth history, when a number of important features of the planet seem to have emerged. So things like the evolution of life, a bunch of metabolisms evolved during this time, but also plate tectonics as we know it, continental crust. A number of features of the planet appear during this time. And so what do we know about the climate during this part of Earth history? And a lot of the drivers of the climate are related to this observed phenomena called the faint young sun paradox. And so we know from observing a number of stars in our solar system that stars like the sun tend to get brighter over their history. So that's what's shown here is just a time scale from 4.5 billion years ago to today with the solar luminosity, the brightness on the y-axis. And so what we can see is we think that the sun has gotten brighter and brighter over history, over Earth history. So we might think that, well, now we should have the warmest conditions on the planet, and back here we have the coldest. But what do we see when we actually look in the rock record? Well, there are some glacial episodes here that stretch back to about 2.9 billion years ago, with some in the late Archean and in the Proterozoic, shown here and here. And so there is some evidence for low temperatures, at least back to about 3 billion years ago. This is contrary to data from sedimentary rocks and specifically using isotope paleothermometers. So I'm going to show a figure next that has a lot on it, so I'll walk you through what this means. And so here's a figure showing, again, for 4.5 billion years ago to today, estimated ocean temperatures based on a number of proxies. And so there are some common proxies that have been used, such as oxygen isotopes in carbonate and chert, that suggest really high temperatures up to almost 100 degrees C back here in the middle of the Archean. We can also reconstruct this thermostability of purported ancestral proteins. It looks like things that were alive then maybe had proteins that were suitable for living at high temperatures. There are, however, a bunch of other proxies, other isotopes in chert, in phosphates, as well as global climate models set against a background of lower solar luminosity that suggests that the Earth was actually relatively cool back then. And you can see that the further back in time we go, the more spread there is in these data. It's hard to say what the temperature was like back then. And so something that's often cited in the literature, though, especially when there's discussion about these temperatures, is people cite these glacial periods as evidence for cool temperatures in the Archean, these periods that I mentioned in the last slide. But I think our understanding of these is a little bit incomplete. So let's spend just a minute talking about where these are today, where we know they are, and maybe a little bit about how long they last. It's one thing to have a really short period of glaciation and its implications for the climate. It's a different thing if we have these really long-lived periods of glaciation on the early Earth. And so there are some glacial deposits that suggest sort of non-hot conditions, but I think most of these are pretty poorly dated, and they're also spatially discontinuous. So the one that gets cited the most often is from this paper here, looking at some glacial deposits from the Archean Mozan group in South Africa, and these are dated to about 2.9 billion years ago. If you look in detail, though, the age dating on these was sort of an average of a bunch of detrital zircons, and so it's not the most precise way to give an age of the deposit and how long that glacial period lasted. As I was reading about this, I stumbled across this paper from the U.S. Geological Survey from 1973 about another Precambrian diamictite in Montana. And at the time, I was a postdoc in Boulder, Colorado, so I decided to go up and check it out. And just to give a little orientation on where this thing is, so this is a Google Earth image of this part of Montana. So here is Bozeman off here, Billings is over here, and these are all in the Beartooth Mountains down here near this little town called Nye, Montana. So these rocks outcrop around here, and it's a pretty awesome area. This is a geologic map from that paper. And the whole area is most famous for the Stillwater layered igneous intrusion. So that's what most of these units are. They sort of strike northwest to southeast across the area. The Stillwater intruded a bunch of older metasediments that outcrop sort of to the south down here. And some of these sediments include what were mapped as glacial diamictites by the survey back in the 70s. And so this is a really simplified stratigraphic column of those metasediments that were intruded by and sort of underlay structurally the Stillwater intrusion. And going from oldest to youngest, the oldest layer here is what I'll show some age dates from. And these are a layered cordierite and hornfels metamorphic rock. And so you can see here in this sort of big piece with a hammer for scale that it records a bunch of layering. This is pretty clearly a metasedimentary rock. There's alternating fine-grained and coarse-grained layers. Here's another smaller hand sample where you can see some of this really fine layering that has gotten preserved, even though the whole area has been thermally metamorphosed by intrusion of the Stillwater. And just as a reminder, that Stillwater is 2.7 billion years old. We know that age really well, and so it helps both with some age constraints. This is a pretty hard minimum age for the rocks we're interested in because they were all intruded by the Stillwater. But we also have to be careful when interpreting any geochron because there's the potential that this could affect the zircon ages we get from this area. Here's a picture of what the diamictite actually looks like in outcrop. And so here's a field notebook for scale. And I hope what you can see is that among the really fine-grained matrix material here, you can see a number of distinct clasts that outcrop here. So this really does look like a classic glacial till or glacial diamictite where we have poorly sorted large clasts that are separated and supported by a fine-grained matrix. Here's another image of something that we've tentatively interpreted as a drop stone. So it looks like there's a bed here that perhaps was deformed as this clast sank out of a melting iceberg or something. It's a little tentative to say, but there are clearly sedimentary features and they are most consistent with a glacial origin for these rocks. So it really does look like we have a glacial diamictite here in Montana. And so from these samples, we've separated out a number of zircons, and here's just a backscatter electron image. This little bar down here is 100 microns. And all these bright grains are zircons, and so you can see a bunch of them we're successful in separating from here. So we're actually able to get detrital zircons out of this. We obtained uranium-lead age dates on the SIMS at UCLA, and I'll show those results now, and I just want to highlight that I'm showing these compared to their thorium-uranium ratio. I'm doing that because igneous zircons typically have this ratio of about 0.8, and that's to help us distinguish from any possible metamorphic grains that were grown during the intrusion of the Stillwater complex. So here's that data shown here. So here's the thorium-uranium ratio, again with igneous zircons plotting about in this range, versus lead-lead age here on the x-axis. So a couple of things you can see. The first is we have lots of grains that are primarily igneous in origin, so this means we can use them for detrital geochronology. And I have the Stillwater intrusion shown here in green. And so from this, we can see that, yes, there's a big range in detrital zircon ages from this unit. And we still have a little bit of work to do processing these, but one thing we can see is they look to be about 2.7, 2.8 billion years old. So you get the age of the rock based on the youngest grain here. And what's pretty cool is this is about the same age as those South African units, something like 2.9 2.8 billion years old. And so we have some more work to do to compare these, but it's looking like there are multiple glacial deposits of about the same age on different cratons, at least preserved today. And so I want to spend my last minute or so here discussing what this means for Archean climate. So I'll bring back this picture of the faint young sun paradox, the way the sun has evolved through time, to suggest that, well, maybe the early Archean was pretty cool, actually, and cooler than we thought. And so then I'd like to propose a couple hypotheses and suggest, okay, what if these glacial rocks, let's say that our age analysis does suggest that they're all about 2.7 billion years ago. So what does that mean? There's a couple things they're coincident with at that time. The first is there's a mantle superplume event that happens here at about 2.7 billion years ago. And so maybe all this fresh mantle material that's erupted onto the surface of the Earth weathers really quickly, drawing down CO2, cooling the planet into its first ice age. Another possibility is that we're also seeing the first evidence for oxygen in the atmosphere. There's geochemical evidence for oxygenic photosynthesis at this time. And what I'm showing here is just there's estimates of the concentration of carbon, CO2, and methane in early atmosphere. Maybe as oxygen comes up due to biologic activity, this methane greenhouse crashes out, causing a cooling on the planet. So it looks like there's a cooling of the Earth that happens about 2.7 billion years ago, maybe related to a couple of these factors. So this age control is important. There's more work to do, and just wanted to leave this up here by saying thanks, and I'm recruiting grad students, so please do get in touch, and happy to answer questions. Thanks.